Okay, thanks for the warm intro, Piao. Thanks everyone for coming. Happy to be here. Okay, let's get started. So in this work, we'll be introducing recursive open meta-agents, or what we like to call Roma for short. And Roma essentially represents a culmination of our research efforts over the past 2 to 3 months at Sentient, building open source multi-agent systems. So I'd like to start this talk off by giving a very, very brief overview of multi-agent systems, and in particular, text-only multi-agent systems. And the reason we're sticking with text is for the purpose of this talk, I feel like it'll be much easier to resonate with text systems and to understand Roma within that context. And also because there is quite a lot of examples out there that you can kind of refer to and compare with. And then I'd also like to touch on the landscape of the closed world versus the open world and sort of give you an idea of what the experience is like building with closed and open source models / agentic systems in practice. So for those of you who are not too familiar, multi-agent systems are essentially a composition of multiple units of intelligence or agents working in concert to achieve a particular goal. In the case of text, these agentic systems usually look like deep researchers, and the units of intelligence or the agents are usually language models or large language models, working to solve tasks like writing reports or synthesizing a bunch of information and compiling them into a particular format or report. And much like large language models, multi-agent systems also have this divide of closed world versus open world, right? Where you have the space being heavily dominated by the closed world and open world sort of trying to play catch up with the closed source models. So on the left side here, you can kind of see the closed world, right? Which contains, all the top AI labs and their deep research implementations of it. And most recently, Moonshot AI's Kimi researcher came out and sort of established or state of the art on most of the benchmarks. Some of you might be wondering why Kimi researcher is in the closed world and not the open world. And as of today's talk and this date, Kimi have not really, or Moonshot AI have not really open sourced anything apart from a technical blog post. On the open world, things are a bit more bleak. There are many implementations of multi-agent systems and deep researchers out there. From our experiences building with these multi-agent systems, none of them have been particularly competitive with the closed world. And overall, just a lot of scattered repos out there, right? But some honorable mentions, we have Open Deep Researcher by Together AI, and then you also have many LangGraph implementations out there by different creators. You also have agentic libraries like Crew AI and Agno, and they have their own sort of implementation. I'd sort of like to emphasize this divide between closed and open world, right? Not just because this is an Open AGI Symposium, but also because it will help you understand why Roma evolved the way it did and why we took the decisions that we did when developing this. Okay. So what was the motivation behind Roma, right? Just like many others, we sort of set out to build multi-agent systems for various use cases, right? Some more traditional, like research and search, and then some that are a bit more native and relevant to our use cases at Sentient, like crypto, market analysis, and market research. And we ended up hitting major roadblocks. With closed source, like many of you know, it's a black box, right? You have a user query, it goes through their system, which many labs kind of go out of their way to hide what actually happens, and then you get the output. So this is great if it fits exactly what you want, but if you're trying to customize it, or if you're trying to do it for a use case that isn't, quite like the exact fit to what they have, it'll be near impossible for you to get results that you want. So we kind of shied away from closed source and went for the more customizable open source sort of approach, or building with open source multi-agent systems. And with open source, we sort of hit 3 fundamental challenges. So if we take a step back and sort of revisit the definition of what a multi-agent system is, it's essentially a bunch of agents working together to solve a particular goal, right? And this sort of implies, the whole working together part implies that there's structure or some meta structure that exists that defines how these agents sort of communicate with each other. And that's sort of our first problem with open source, right? Because many of these open source libraries sort of prescribe a structure based on what the creator thinks that should be, right? So it's different across many libraries. So for us, finding the right topology was a big sort of question that we had to sort of answer. The second part was transparency. Although these are open source, depending on which, depending on what the repo or the creator prescribes as a structure, the interactions were opaque, and there wasn't, like, it was very hard to debug, and we couldn't see what's going wrong if things went wrong. The last part is flexibility, which means if we got to the point where we have a use case which works well, we're kind of stuck because we can't really extend this use case to other use cases because they don't quite generalize, right? It's just a prescribed structure by the creator and doesn't necessarily work on other use cases, which meant we went back to the drawing board and back to square one where we had to worry about the same problems over again. So essentially, most of our time was actually just spent on structure rather than understanding the agents themselves. And just kind of to drive the point home, our experiences building with open source kind of look like this visual on the left, where like the structure is some variation of this. And so our claim was that structure shouldn't be the hard part. There should be an intuitive structure that exists out there that's general and flexible enough for many use cases, right? While enabling creators or users to sort of be able to debug and understand it and understand the flow very well. And that structure looks like that, which is kind of what Roma looks like, and that's sort of foreshadowing on what Roma will look like. Yeah, so it has this sort of hierarchical, recursive decomposition thing going on. So we decided to validate this hypothesis by tackling search. And the reason we went with search is because it's a well-established problem. There's a lot of literature within agents and multi-agent systems. And because also there are also quite a few benchmarks out there that have been heavily scrutinized, one of which is SEAL0, which Tu presented in the previous slide. So our goal was very simple: build a competitive multi-agent search system using Roma. And the baseline that we used is actually O3 Pro with search. And the reason we went with search, which is like ChatGPT search or GPT search, right, is because there aren't really that many scalable open source alternatives for search tools out there. So we ended up using the search tool from ChatGPT, and we decided to baseline it against O3 Pro, which is one of the better models that ChatGPT or Open AI have. The rest of our setup, though, remains faithful to open source mission, right? We integrated a mixture of open models like K2 and DeepSeek R1, which are some of the more capable models out there. And we deliberately decided to avoid over-engineering or like prompt optimizing to do well on a particular task, right? So the whole emphasis was just to verify the claim of topology or structure rather than tweaking components and over-engineering. So you might remember this graph from the previous presentation or some modified version of it. And you can see here that the benchmark is quite heavily dominated by closed source models, right? Probably the leading 8 entries are all closed source. And then you also have open source, right, playing catch up and not really actually doing anywhere near any of the closed source models. And just one thing to point out here is that some of these models are single agent systems and others are multi-agent systems, right? So it's not quite fair to compare all to each other, but we left them as a point of reference. And then you sort of have Roma, right, where the structure that we decided to verify ended up doing much better. And I'll go in a little bit into how Roma works in a bit. But I just want to point out that we started off with our baseline model, which is at 18.9, and we ended up with 45.6 using the same search tool, right? So if we replace O3 Pro with search with Roma with search, we're going to see this 26% improvement. And just to give you an example from SEAL0, for example, we have this question, which is who is the purchaser in the largest confirmed merger that ultimately failed to complete? And the ground truth answer here, if you look at this Wikipedia page, is actually AstraZeneca in 2020. And the deal failed at a valuation of 232 billion due to the COVID pandemic and a lack of interest, right? And so if we look at one of the closed source models, and this is sort of also, will shed light into how the problems we face with closed source models. You see the answer, and the answer is incorrect, right? It says this is Pfizer. And if we go back here, you see that Pfizer is ranked third with the year 2015, 160 billion, and the deal fell through due to tax inversion. Anyway, so we see here that it got the wrong answer, right? But if we were to assume that that's the right answer, it did get the right valuation, but it also got the date wrong. It said 2016 instead of 2015. And that's sort of all the information you're going to get from a closed source model, right? So when you have a use case like that, and it's wrong, this is all you can tell. And you can't really tell why it got it wrong or why it's hallucinating, if it is hallucinating at all, or if the sources it got are incorrect. While Roma, right, will give you, or it does answer correctly, it gets the date correct, the valuation correct, and also the reasoning correct, right? And this is just a sort of distilled version of the actual full report that it generates. And this can be customized, by the way. I'd like to show a live demo of how Roma works, because if you've made it this far, you're probably wondering how it works and why it works. So I have a very simple example here that I'd like to sort of refer to just explain how it works, right? So this is another question by Seal0, and the question is, what is the current age of the last American physicist to win the Nobel Prize in Physics, right? On a very high level, the way information flows in Roma is there's top-down decomposition, and then there's bottom-up aggregation, and there's also left-to-right conditional flow. So left to right is not always necessary. But let's do sort of a quick dry run of how this works, right? So we start off with this root node, which is the original task, and it goes through top-down decomposition. So it goes through something called an atomizer, and the atomizer's job is basically to decide, is this task simple enough that a normal LLM can basically execute, or is it complex and needs to be broken down, therefore planned and made into different subtasks? So in this case, the LLM decides or the atomizer decides that it's not atomic, it needs planning. So it goes through and generates different subtasks, right? And these subtasks ideally should work towards achieving the final goal. So now we have a bunch of specific subtasks, like search for the most recent American physicist, and then search for their birth date, calculate the age, and then write the final answer. So here, if we look at this node in particular, calculate the current age, right? This is conditioned on the past two nodes, right? So it can't really run unless it knows who this person is, who this physicist is, and what their age is, right? So if we take a look at what this search result shared or got, it'll tell you that the person in question is John Clauser. And then it finds John Clauser's birth date, and then it'll pass all this information here to this node, and this node will start calculating John Clauser's age, right? It uses code in this case, and it'll give you the result of 82 years, right? And that's actually the correct answer. So this is sort of an intuitive way of how this Roma system works. And then once these are completed, the subtasks are completed, you have bottom-up aggregation. So this root node will look at all the results of these nodes, right? And we'll try to answer the original task it had given the answers from these. And you'll see here that it will give you the final answer. It'll tell you John Clauser is currently 80 years old as of August 2. I calculated this 2 days ago, so that's why there's a bit of a discrepancy there. So this is recursive, right, and parallelizable as well, right? So it's the same logic for every node, and if nodes don't depend on each other, they can be calculated all together all at once. Another example I'd like to show is from Humanities Last Exam, and the reason I'm showing this example is not to sort of scare you with Humanities Last Exam, which is a notoriously difficult benchmark, but rather to show you sometimes going deeper, right? So this is very simple in terms of it only broke things down once. But are there instances where going deeper than breaking down once, where those are beneficial, right? And in this case, on very difficult problems, we sort of calculated the same. We've done Roma twice on the same question, once on depth 1 and then once on depth 2 to see what happens. I don't want you to get too caught up on the question because it's a very difficult question that I myself don't really know like the answer to too well, but like it's just consider the following polynomial. What's the natural density of the set of prime numbers p such that that polynomial remains irreducible b mod p, right? And the ground truth answer here is 2 over 7. But if we look here, right, the system decides not to break things down, oversimplify things, so it doesn't really get the correct answer, right? It either hallucinates missing information or just flat out gets it wrong. And you can see here the final answer that it gave is actually 1 over 7, right? But if we look here at this example, which is way more fine-grained, right? You're going to see that it's actually trying to compute a lot of different things and trying to gather a lot more information. And in this case, it'll give you the correct ground truth answer, which is 2 over 7, right here. So it unequivocally says 2 over 7. Back to the slides. So that's just a little demo of like how things work. Then sort of to further verify that Roma works, we've decided to test it on other benchmarks as well. So Frames is a benchmark that was released around a year ago by Google DeepMind. And Frames basically tests agentic capabilities or search engines, search augmented large language models on multi-hop questions. And you can think of multi-hop questions as questions that would require you to sort of do multiple Google searches, go through some Wikipedia pages, get some information, and then use that information to answer. So you can also see closed source models, right? You have Kimi Researcher sort of dominating the benchmark. And then we can see Roma actually performing better than Kimi Researcher compared to the baseline, which is GPT-4o search, right? We see also quite a huge improvement. Similar with Simple QA. Simple QA is a benchmark by Open AI. This benchmark, as the name insinuates, is more about answering simple questions. So multi-agent systems aren't really going to do that much better than agentic or single agent systems, right? It just involves really searching for a question and answering, but we still perform competitively, right? We're kind of close to a lot of the state of the art and, trailing by a very small delta. So in summary, that's what Roma is. It's basically, we're dictating a standard topology for many use cases, right? And we're claiming that this topology is interpretable, composable, and very easy to iterate on top of. We're stripping away structure from building these models, and we're saying this is the structure that should be used, and we believe that this structure is suitable for many use cases and tasks, right? And this opens doors for many different things. For enthusiasts, explorers, and builders, essentially they can vibe prompt their way into whatever use case they want, right? Because they don't have to worry about structure or setting things up. All they have to worry about is like how the aggregator aggregates information or how the planner plans, right? So, and these are essentially agents just with particular prompts. And they can contribute and explore different use cases given the reduced barriers to entry. And also, what's really interesting is that they can experiment with many different tools and mix them together, right? This is not just a deep researcher. I just wanted to use deep research as an example to bring the point home about Roma. So you can go with code interpreter, bug finder, video generator, image generator, comic book generator, whatever you think is useful for you. And for researchers, there's a lot of interesting use cases and that they can sort of explore, right? They can focus on pushing the boundaries of context engineering, agent design, exploring things like breadth versus depth, and many others. That's pretty much the talk. Our work is heavily inspired by some projects like our own Open Deep Search and Right Here, which is a project by Jürgen Schmidt-Huber's lab. Yeah, thank you guys.
Thank you for the presentation. Recently, I have looked into a lot of open source, deep research implementations. And it turns out that a lot of those are actually based on a iterative manner, and few are based on a recursive manner. However, from the perspective of a problem solver myself, I guess a recursive is a more natural and the go-to approach to come up with a solution for a really difficult problem. So you mentioned that the system is able to do a two-level, like recursive breaking down of the original problem. Have you seen scenarios in which there's more levels of recursive delegations?
Yeah, that's actually a very good question, right? First of all, I do agree with the part that the structure, recursive structure, is more naturally occurring to us humans, right? I mean, if you have a CEO has a task, right, they'll probably pass it to VPs, VPs will pass it down, and this sort of cycle continues, right, to answer things. In terms of depth greater than 2, we haven't really encountered questions yet that sort of require depth higher than 2, although, you can keep going to infinity with recursion. But I think that's also one of the big research questions that sort of stem from this, is like, what's the sort of sweet spot between breaking things down and keeping them, coarse-grained for LLMs to answer, right? Because LLMs are also becoming more capable. So, yeah. I wonder if there are cases that are not deep research or text-related, maybe video generation, where this would work, right? If you had to generate like an hour-long video, if you can keep breaking down to like small scenes, like what had happened. But yeah, does that sort of answer the question? Yeah.
Another question I have is, I think the key to this recursive approach is to how to decide in which way to break the original problem down to different atomic questions. I was wondering, in this part, do you guys have any observations or takeaway, or is it just a simple prompt engineering?
Yeah, so far it's been mostly very simple prompt engineering just to test the thing out. But I think finding a way between, of generating subtasks that are like sort of mutually exclusive, collectively exhaustive, that would be the right way to go. But getting there, I'm not sure how to do that yet, but I think we're actively working on that. And it's also probably an area of research that we should explore.
Are you guys open sourcing this recursive approach?
Yes, soon. By the end of the month, for sure, it'll be out. So you can, you'll get this basically. You can do whatever you want with it. Yeah.
Awesome.
Yeah.
Okay, great. We have to cut questions short because we're running a bit out of time. Thank you, Salah.